Welcome to our tutorial on Rust generics and type parameters. These are powerful features that allow you to write flexible, reusable code in Rust. Think of generics as a way to create functions or structs that can work with different types of data. For example, imagine writing a function that can sort any type of collection, whether it's integers, strings, or custom structs. In Rust, you use angle brackets to define the generic types. Let's take this simple function. Here is a type parameter that can be any type that implements the trait. So whether you pass in integers or floating point numbers, it works seamlessly. This flexibility greatly enhances your code's reusability and maintainability while keeping performance high. Welcome to our exploration of generics in Rust. First, we'll introduce the concept and why it's useful. Next, we'll dive into type parameters, those mysterious placeholders that help us write flexible code. Then, we'll show you how to define generic types and functions, making your programs more versatile. We'll also cover trait bounds and associated types, which allow for powerful constraints on these generics. Real-world examples will bring everything to life, and we'll compare different approaches too. To test your understanding, we have a quick quiz on type parameter basics. Finally, I'll summarize what you've learned today. Let's get started. Hey there! Today, we're diving into the world of generics in Rust. Generics are like magic tricks for your code. They let you write functions and structs that can work with any data type, not just one specific type. This means you can create reusable, versatile components without sacrificing safety or performance. For example, imagine a simple function to find the maximum value from a list of numbers. With generics, this same function could also compare strings for lexicographical order. Let's take a look at how it works. Say we have a generic function called. It takes any type that implements the trait and returns the largest one. So whether you pass in integers or characters, will do its magic to give you the maximum value. Generics are your Swiss Army knife for building robust and flexible Rust code. Welcome to our next step in understanding generics and type parameters in Rust. Let's dive into defining a generic function. In Rust, we use the letter T as a placeholder for any data type you want to pass to your function. This is called a type parameter. Our example here defines a function that takes one argument of type and returns it unchanged. Here's how it looks in code. Notice the dash symbol. This specifies the return type, which is the same as the input type. This means no matter what type you pass, be it an integer, a string, or even a custom struct, the function will simply return that exact type. Pretty neat, huh? Let's try calling our function with some different types to see how it works in practice. Now, let's take a closer look at running the identity function. This function is particularly interesting because it returns exactly what you put into it. No modifications or transformations. In our example, we're testing this function with two different types, strings and integers. When we run identity with the string hello, it simply returns hello. Similarly, when we pass in the integer 42, it returns 42 unchanged. This makes the identity function incredibly useful as a utility in your code. For instance, you might use it to ensure that data types match at certain points in your program without altering them. Let's see how this looks in Rust. This code snippet demonstrates the function working with both a string and an integer, showing how versatile it can be. Welcome to our exploration of type parameters and constraints in Rust. You've probably heard about generics, but how do we actually limit the types that can be used? This is where the clause comes into play. Let's dive into an example. Imagine you're working with a generic function called, which takes two values of the same type. But not any old type. Let's say we want to ensure that must implement the trait. This means that can be copied without moving ownership, like an integer or a string slice. So in your code, you'd add. By doing this, Rust knows it's safe to copy the values inside the function, ensuring that your program runs smoothly and predictably. Alright, let's dive into using trait bounds in our code. Trait bounds allow us to specify which traits a type must implement when we're working with generics. In the example on this slide, we have a function called that takes any type as long as it implements the trait. This means we can print out values of different types as long as they can be formatted to display. For instance, if you call it will work because integers implement. But if you try with a type that doesn't implement this trait, like an array or struct without the necessary method implementations, it won't compile. So, using trait bounds gives us more flexibility and ensures our generic functions behave correctly for any compatible type. Alright, let's dive into our next slide. Here we see the function in action. The beauty of Rust generics is that this function can now work with any type that implements the trait. This means you can print values of different types without having to write separate functions for each one. For example, we have a simple integer 42 and a string hello. Both are printed using our generic function. The magic happens because Rust infers the type at compile time. So whether it's an integer or a string, handles them seamlessly with just this single definition. This flexibility is one of the key benefits of Rust generics in your toolkit. Alright, let's dive into today's quiz question. Imagine you're working on some Rust code that involves generics. Now, if you forget to add the trait bound somewhere it's needed, what happens? Well, Rust won't know how to format and display that value properly. And as a result, your code won't compile. You'll get an error at compile time. It's like trying to print out a secret message but forgetting the special ink needed to make it readable. So, remember, when dealing with generics in Rust, always ensure you include the necessary trait bounds for display or any other operations you intend to perform. Welcome to our exploration of Rust generics. Today, we're going to create a generic struct that can hold any type of data. Let's dive into how this works with an example. A stack structure. A stack is a last-in, first-out, LIFO data structure commonly used in programming. To make it versatile, we'll define our stack as a generic struct using Rust's generics feature. Here's the code for our struct. Welcome to our exploration of Rust's generics and type parameters. Let's compare two approaches. First, we have the hard-coded types in struct definition. Imagine you're building a simple program that needs to handle both integers and strings. If you use hard-coded types like this, your code might look something like this. But what if you also need strings? You'd have to duplicate your struct or create multiple structs. Now let's contrast it with using generics with trait bounds. This is where Rust shines. By defining a generic struct like you can pass in any type when you use this struct, such as or, it's more flexible and reusable, making your code cleaner and easier to maintain. Generics with trait bounds allow for powerful and dynamic type handling, exactly what Rust was built for. Welcome to our next step in exploring Rust generics. Remember, generics allow us to write code that can work with any type of data. Now let's see how this works with stacks. We've initialized a mutable stack named stack using the method. With generics, we don't need to specify the exact type right away. It's smart enough to handle different types on its own. We push an integer 42, and then the string hello, onto our stack. Finally, let's check what's in our stack by printing its contents with. When you run this code, you'll see stack contents 42. Hello everyone. Today we're diving into two powerful concepts in Rust: associated types and trait objects. Let's start with associated types. Imagine you have a collection that can store any kind of data, but the way it handles the data might differ based on the type stored. That's where associated types come in handy. They allow us to define types within traits, giving us more flexibility in our code design. For example, if we create a trait for a collection, we can define an associated type like that specifies the type of items this collection holds. Now, let's talk about trait objects. Trait objects enable you to work with multiple types that share a common interface. Think of a function that takes a trait object as an argument. This function could then work with any type implementing that trait. This is incredibly useful for writing generic code or handling polymorphism without needing explicit type information. By combining these concepts, Rust offers robust and flexible programming paradigms. Welcome to our journey into the world of Rust generics. Today, we're diving into associated types. Let's take a look at this example. We define a trait. Notice how it has a type parameter called. This is key because it allows us to specify what kind of data will be produced by each call to. For instance, if you have an iterator that deals with numbers, it could be, and for one that works with strings might be. The method returns an meaning it can return a value of the type specified by or none at all. This flexibility is what makes generics such a powerful feature in Rust. Great job! Now let's take a look at our example. Notice that the trait defines an associated type called. In this case, we're returning values. Our struct keeps track of its current value and increments it each time is called. If the current value is less than 5, it returns a, otherwise it returns. After running our code, let's see what output we get. First 3 items are 0, 1, 2. That's because each time is called on our mutable variable, the current value is printed and increment. This shows how iterators can be used to generate a sequence of values in Rust. Hey there, fellow coders. Welcome to this quick dive into associated types in Rust. So what's the big deal about associated types? Well, they're like the secret sauce for making your code more flexible and reusable. Imagine you have a trait that defines an operation, but instead of just defining a single type, it allows you to specify multiple related types. That's exactly what associated types do. For example, if you're working with collections in Rust, you can define a trait with an associated type like, which represents the type stored within the collection. This way, you can write functions or methods that work with different kinds of collections without knowing their exact internal structure. So, by using associated types, you unlock the power to create more dynamic and versatile code. Ready for a quick quiz to test your understanding? Let's get started. Welcome back, everyone. Today we're diving into the key takeaways from Rust generics. First off, what are they good for? Generics allow us to write code that works with any type of data, like a Swiss Army knife, but for coding. The symbol is your go-to for representing these types in functions and structs. But wait, there's more. You can add trait bounds to these type parameters to specify the kind of operations allowed on those types, like ensuring something can be printed or copied. And for an extra twist, you can even define associated types within traits to create interfaces that are both flexible and powerful.